Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. So today we're going to be working on the question on the screen. First, we're given an equation where ethanol reacts with oxygen to give us carbon dioxide and water. This particular reaction is called a combustion reaction. And we're given the change in internal, sorry, yeah. So we're given the change in internal energy of the reaction to be negative 1373 kilojoule per mole at 298 kelvins. And we're asked to solve for this particular thing, which is the change in enthalpy for the reaction. So the first thing you have to do is for you to write out the equation that connects both internal energy and enthalpy. And it is this equation here. So change in enthalpy of the reaction minus the change in internal energy of the reaction equals change in the number of gases for products and reactants for the reaction times the gas constant times temperature. So this is what you get, right? So this is basically what you have. So you have the change in the number of gases for the reaction times R times T. So yeah, this is basically what you do. So the first thing you do now is, since we already have been given this side of the equation, which is a change in internal energy of the reaction, and we're asked to solve for what is on the right. Well, what we have to remember is we need basically math. We need to determine what is on the right side of the equation. So the first thing is for you to note what this change in N right here, what this is, right? So the change in the number of gases is just basically for you to count how many gases for the product and how many gases for the reaction. So you're going to have the final state of the reaction. So Ng of F, okay, minus the initial state of the reaction, Ng of I. So basically the number of gases for the left side of the equation, sorry, the number of gases at the final state is for you to just basically, we're going to determine that by counting it, right? So currently we have 2 molecules of carbon dioxide and then 3 molecules of water H2O. So that would be 2 plus 3 is 5. So that is the number of gases for the final state. And then that minus the number of gases for the initial state. So before the reaction occurred. And we see that ethanol is not a gas, so we can't count that. But we reacted ethanol with oxygen gas, and we had to react it with 3 molecules of oxygen gas in order for the reaction to take place. So that's going to be 5 minus 3. So change in the number of gases for the reaction is 2. So we have that information right. So yeah, that's just basically what you do. So rewriting what we have, we're just gonna rewrite this. So we just basically will solve this. Let me use a different color. We have change in Ng, RT would now equal 2, okay, times the gas constant, which is 8.3145 joule per mole Kelvin, okay, times whatever this temperature is, which we're told is 298 kelvins. So of course we cancel out the Kelvin, we cancel out the Kelvin. So what you end up with is 2 times 8.3145 times 298. So what we end up having is 4955 comma, oh sorry, dot 442 joules per mole. Okay, of course, Kelvin has been cancelled out. So this is basically what you get. And this is the information that you're going to actually use and substitute in order for you to determine the change in enthalpy for the reaction. But before we go there, we have to remember that the change in internal energy of the reaction was given to us, which is negative 1373 kilojoule per mole. We're given that value in kilojoules, and we have our current information in joules. So we have to go from joules here to kilojoules. So we just simply divide by 100, and we end up getting this information right here to be 4.95544 kilojoule per mole. So that is basically what is going on here. So the next thing we have to do is for us to rewrite the equation up top. So we have the change in enthalpy of the reaction equals the change right here, this change value of gas constant RT plus change in internal energy of the reaction. So yeah, that's basically it. So we substitute what we have here, the change in enthalpy of the reaction equals 4.9554 kilojoule per mole plus, and then change in internal energy, we have that to be negative 1373 kilojoule per mole. So that will be negative 1373 kilojoule per mole. So of course, change in enthalpy of the reaction is just going to be 4.95544 kilojoule per mole minus 1373 kilojoule per mole. And when we input that information in the calculator, we're going to end up getting negative 1368.045 kilojoule per mole. Remember that the change in change in the number of gases for the reaction times R times T is just simply 4.9. It's a very small number in comparison to 1373. So basically, this is just basically what is going on. That's why we still have a large number, because the multiplication of the change in the number of gases for the reaction times R times T gives you a small number, and then you're dealing with the internal energy, which is a large number. So we end up having a large number for the change in enthalpy for the reaction. So that's basically all that is going on here. But let's not forget that we're given this particular question in four significant figures. So we're going to stick to making sure that work is left in four significant figures. So that would end up being change in enthalpy of the reaction equals negative 1368 kilojoule per mole. So this is basically the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the value of change in H minus change in U for the reaction C6H12O6 plus 6CO2 dash 6CO2 gas plus 6H2O at 298 Kelvin. Of course, you're going to be wondering, okay, what did she just read? Well, this is a chemical equation, as you can see on the screen, and we are asked to calculate this information here, which is change in H of M minus change in U of M, and we're asked to calculate what the answer for this value is and for this particular equation. Well, before we do anything, you have to note that the change in H of M minus change in U of M equals to the change in N of gas RT, where change in N subscript G is the change in amount of gas molecules in the reaction. In the reaction. So that's basically what this particular symbol is that I just wrote the information down. So the first thing you have to do is for you to determine change in NG first. So when you have this information, that's what you have to do. Well, what that is going to mean is that the number of gas molecules for the final minus the number of gas molecules for the initial part of the reaction. Of course, the final part of the reaction is the product side, and the initial part of the reaction is the reactant side. So you have to count the number of gas molecules, and you have to subtract the final number of gas molecules from the initial number of gas molecules. So changing Ng equals the product is 6CO2, that would be 6, minus the initial side is 6 right here. So this is the change in number of gas molecules equals 0. Now the R that we have here is 8.3145 joule per mole Kelvin, and then temperature is 298 Kelvin. So that's basically what this is. So of course, now the next thing we have to do is to substitute in this equation right here to get our answer. So we end up with change in H of M minus change in U of M equals 0. So the change in number of gas molecules times the R 8.3145 joule per mole Kelvin times temperature, which is 298 Kelvin. So when you multiply everything, you have change in H of M minus change in U of M equals 0. So this is basically the answer. Of course, this is just what this question is giving us. Another question, you actually have a value that is not 0. So, or you have a negative value. So you can either have a positive value, a negative value, or 0 value, depending on how the equation goes. Some equation will give you a different value for the change in H minus the change in U. Salam and welcome everyone. So today we're going to be working on the question on the screen that says the standard enthalpy of formation of phenol C6H6O is negative 165.0 kilojoule per mole. Calculate the standard enthalpy of combustion. So the first thing you have to note is this: you have the question telling you that a reaction has taken place, which is C6H6O liquid has undergone a combustion, which is just whatever the molecule is plus oxygen gas. So it reacts with oxygen gas to get carbon dioxide and water. So this is what happens in all combustion reaction. An organic compound reacts with oxygen to give you carbon dioxide and water. So the next thing you have to do is to just balance the chemical equation. Of course, you are going to get the liquid. Sorry, you're going to get oxygen. The phase for the oxygen gas is gas phase. Carbon dioxide is a gas phase. But in the case of water here, it's a liquid. So yeah, that's it. So phenol reacts with oxygen gas to give you carbon dioxide gas and liquid water. So that's it. The next thing you have to do is to balance the chemical equation. So I'm going to do that right here. To balance it, we have to make sure that what is on the right side, the number of atoms on the right side, matches the number of atoms on the left side. So I put 6 in front of carbon to make sure I balance the carbon. I put a 3 in front of hydrogen to make sure I balance hydrogen. So hydrogen is also balanced. So just oxygen left. So you have 3 oxygens on the right and then 12 again. So 12 plus 3 is 15. So in this case we have just 3. Well, if we put a 7 here, 7 times 2 is 14 plus 1 15. So we have the carbon, the hydrogen and the oxygen balance, and this is simply the balanced chemical equation. So using this information, we can now calculate the standard enthalpy of combustion. Note that the standard enthalpy of combustion is the same thing in this case as the standard enthalpy of reaction. Because a combustion is a reaction, we can just substitute the standard enthalpy of reaction with the standard enthalpy of combustion because it's basically the same thing. So just putting that in mind, we can now write the equation that we'll be using. So the standard enthalpy of combustion to be equal to the sum of the standard enthalpy of formation, okay, minus the sum of the standard enthalpy of formation as well. So you may be wondering, why are we subtracting the same thing? We're not really subtracting the same thing because here we're dealing with products first. So we're going to be dealing with the standard enthalpy of formation for products, and then we're going to do minus the standard enthalpy of formation when you add them all up for reactants. So basically, this is a summation symbol. So you're just going to add them up. When I do more of the problem, I'm going to like explain it to you guys bit by bit. So rewriting all of this information, we have the standard enthalpy of combustion is going to equal whatever it is for the product. So you have 6 times the standard enthalpy of formation for carbon dioxide gas. So this CO2, right here has a coefficient of 6. So 6 is going to have to come out here, okay, plus, because the summation is telling us that we're going to sum things up, plus 3, okay, times the standard enthalpy of formation for H2O liquid, okay. It's very important that you don't mess up the phase because H2O liquid, H2O gas, H2O solid will give you different values when you go on to check the standard enthalpy of formation in your resource section of the book, or if you go on Google, you're going to see that you have different values. So make sure that you're putting in the right phase whenever you're doing this portion of the work. So minus, because now we're done with the products, now we have to do with the reactant. So minus the standard enthalpy of formation, okay, of the of basically C6H6O liquid, okay, plus the standard enthalpy of formation for O2 gas. So that's basically what we have. So yeah, standard enthalpy of combustion is going to be 6 times the standard enthalpy of formation of CO2 gas is just 6 times negative 393.51 kilojoule per mole. Now, before we go on further, let me explain to you what's going on here. You see the standard enthalpy of everything that I'm underlining with the wavy line, they have an exact value. You would have to go to the resource section of your book, right, as I'm doing this work, and you're going to be checking them out. So that is what I'm not going to write all of that information out here for you guys, because I want a situation where you guys will be able to like answer questions without depending on me explaining it. So you have to go to the research section of your book to find the standard enthalpy of formation for CO2 gas, for H2O liquid, for phenol C6H6O liquid, as well as for O2 gas. When you have that, then you can substitute, which is what I'm doing. If you don't know where to find it in your book, it's usually at the back of your textbook, or you can go on Google and like as I'm working on this, have like open another tab on your phone or on your computer and be googling it, and you're going to see that I'm putting in the exact value. And if you don't want to use your phone, please use your textbook. So plus, okay, plus 3 times the standard enthalpy of formation for H2O liquid is, looking at my textbook, is 3 times negative 285.83 kilojoule per mole. Okay. Minus, okay, minus again, because the standard enthalpy of formation for phenol, well, we're not given that. And actually, we were given that, meaning this is the whole point of the question. The question says the standard enthalpy of formation of phenol is this, meaning it's possible that you don't find that in your textbook, right? So this one was actually given to us. And so this is the value we're going to use. We're not going to use what's on the textbook for now. We're going to use this value that we're given. So that's going to be minus 165.0 kilojoule per mole. So make sure you also always go back to your question, right? Okay. Sorry, not a bracket. I meant to write a plus. Plus the standard enthalpy of formation for O2 gas. And we see that to be 7 times 0, because that's the standard enthalpy of formation for O2 gas is just simply 0. So we just basically work on this. So 6 times negative 393.51, that's just basically negative 2361.06, okay, kilojoule per mole, plus the other product 3 times negative 285.83 kilojoule per mole is just simply going to give us negative 857.49 kilojoule per mole. Okay, so that's it. And then you have minus minus, which I can just call plus 165.0 kilojoule per mole. Of course, 7 times 0 is 0. So yeah, so change in enthalpy of combustion is going to now equal negative 231. Sorry, change in enthalpy of combustion is now going to equal negative 2361, okay, 0.06 kilojoule per mole plus 857.49 kilojoule per mole. So that's going to give you, give me a second. You know what I just realized? I just messed up. I put a plus here, which is importance of like looking back at your work. I put a plus here when 3 times negative 285, when I should have put a minus here. So that would be negative this, negative that. So negative 2361, because negative 393.51 times 6 is what this is, plus negative 285.83 times 3. So I'm supposed to get a negative 857.47 kilojoule per mole. This is important. This is the reason why you have to focus on not making mistakes and consistently cross-checking your work. So you have negative 3218.55 kilojoule per mole, okay? Plus 165.0 kilojoule per mole, okay? Change in enthalpy of combustion is now going to equal negative 3053, okay, 0.55 kilojoule per mole. So if you go back to the question, you would see that we're giving our question in 1 decimal places. So 1 decimal place. So we have to do the same thing here. We have to do it in one decimal place. So what's going to just happen is me going to rewrite the answer in one decimal place. So that's going to be negative 3053.6 kilojoule per mole. So this is the answer in one decimal place. So this is basically how you do this problem. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the change in enthalpy of reaction as well as the change in internal energy of reaction at 298 Kelvin for the reaction carbon in basically graphite plus H2O gas react to form carbon monoxide plus H2 gas. So to solve this question, we have to first of all write out this particular equation or formula, which says the change in enthalpy of reaction is going to equal the sum of basically this. Hold on, I'm just going to write it out and I'm going to explain the formula for you. So you would observe that this equation is just you repeating this and this. So basically, I'm writing that two times, but there is no problem with this equation. It's just that the first part is when you're dealing with products, and the second part is when you're dealing with reactants. So what this particular formula is just telling you that when you're trying to determine the change in enthalpy of reaction, you're going to first of all sum up the change in enthalpy of formation for the products, and when you do that, you're going to sum them all up or just basically add them up. And whatever value you get will be minus the sum of the change in enthalpy of formation for the reactant. So we're going to use this question in order for you to get the question properly. So first of all, you have this formula now. So I'm going to write it out as we applied to answering this question. So I'm going to put it down. See, change in enthalpy of reaction is going to equal the product. So we're going to just first of all say the enthalpy of formation, okay, for enthalpy, okay, I'm going to bracket it of CO gas plus, so don't forget we're summing it up, the change in enthalpy of formation for H2 gas, okay, a lot of information, we add them up, and then that minus the change in enthalpy of formation, which is right here. So that will be change in enthalpy of formation for carbon graphite. Okay. Plus, don't forget we have the summation for a reason. Change in enthalpy of formation for the H2O gas molecule. Now, make sure you pay attention to everything that you're giving. Make sure you pay attention for the phase of the reaction, because this particular case now we're seeing that we're dealing with H2O gas. A question can come when you're dealing with H2O liquid. So just pay attention there, because there are some times whenever a molecule can take both the liquid phase or the gas phase, or sometimes when the solid phase, the value would differ based on all these phases. So make sure you pay attention to the phase that the reaction occurs. So you can see that I've written all of this out. I'm just basically writing it out little by little. So before we go on to solve this question, I want to put some information that will be very useful to you. Some of you may not have the resource section of your book, or the part of your book that of the Atkins physical chemistry book that would show the different change in enthalpy of formation for different molecules that we're going to be studying in the book. So in case you don't have the Atkins book, you can just type the change in enthalpy of formation for carbon monoxide gas on Google. That will give you what you need. So in this particular question, I'm just going to give you all of them, and then we're going to use that information to basically solve the question. So yeah, that's very, very important. That's basically the information. So of course, we're going to just simply substitute. Okay. So we're going to substitute one by one, one by one, one by one. So changing enthalpy of the reaction is just simply going to be this one here. The carbon monoxide is just, we're going to substitute it. So that would be negative 110.53 kilojoule per mole. Okay. Plus 0. Okay. Minus changing enthalpy for carbon graphite is going to be 0. Okay. Plus, we're dealing with formation. We're on this one here now. We're on the last one. So that's going to be changing enthalpy of formation for H2O gas. So that's going to be plus negative or let me use red pen so we're consistent. That's going to be negative 241, okay, 0.82 kilojoule per mole. So that's basically what's going on. So we move on. So change in enthalpy of reaction is going to be negative 110.53 kilojoule per mole. Okay. Minus and then plus minus. So that will be minus plus minus is just going to give you a big plus, and then that will be 241.82 kilojoule per mole. So having this information, we have change in enthalpy of reaction to now equal 241.82 minus 110.53. So that's going to give you 131.29 kilojoule per mole. Okay, so that's basically the answer to this question. So yeah, that's how you solve it. No issue, super easy, super duper easy peasy. So going back to the question, we've seen that we've been able to successfully answer one question: change in enthalpy of reaction. Now we have to know the change in enthalpy. Sorry, now we have to know the change in internal energy of reaction. So now we're supposed to solve for this change in internal energy of reaction. Now the first thing you have to note is this formula I'm about to write is what you need anytime you're giving maybe enthalpy and change in enthalpy of reaction, but you're not giving the change in enthalpy, sorry, change in internal energy of reaction. Basically, when you know the value of one, you're going to know the other value. Just you making sure to use this particular equation. So the equation is change in enthalpy of reaction minus change in internal energy of reaction equals N, changing Ng, RT, where change in Ng is simply the change in the number of gas molecules. So that's basically what's going on here. So I'm going to first of all rewrite the equation down here so nobody needs to go back. I don't need to go back up and no one gets confused. So just rewriting the equation plus, I promise you this is important for me to write. So that's going to be CO gas plus H2 gas. Okay, so now we already know this part of the question, right? We already know this value because we just solved for it. We're trying to find change in internal energy of reaction, and we need to now know this value. By the way, temperature is what T is, and R is basically gas constant, okay? Gas constant. Now you're going to be wondering what is change in Ng or change in number of gas molecules. Well, it's just going to be the number of gas molecules at the final state minus the number of gas molecules at the initial state. So that is basically what this is showing you. So that's going to be number of gas molecules for the final state minus number of gas molecules for the initial state. So for the final state, you see, going back to our equation, this is the reason why I was writing the equation in the first place. We have one gas molecule for CO and then one gas molecule for H2 gas. So we have two gas molecules here. That's finally after the reaction is taking place. Now, for the reactant, before the initial reaction occurs, we have just one H2O gas molecule. So 2 minus 1 is 1. So this answer is 1. So basically, changing number of gas molecules times R times T is equal to 1 times 8.3145 joule per mole Kelvin times 298 kelvins, right? So so basically this information here equals, going back to our work, of course, we can cancel out kelvins. So 8.3145 times 298 will give you 2477.72 joule per mole. Sorry, I was about to write kilojoule, just joule per mole for this question. So yeah, that's basically the answer. Now, of course, because our question is to find the change in internal energy of the reaction, and we have this, we just have to rewrite the formula. So rewriting the formula, we have so having this information, we have changing enthalpy of reaction to be 131.29 kilojoule per mole, and then change in NGRT. Well, in this particular case, we have our information in joules per mole. So going from kilojoules, from joules per mole to kilojoules per mole, will just involve us dividing by 1000. And if we do that mentally, basically in our brain, we get 2.4772 kilojoule per mole, okay, equals change in internal energy of reaction. You can see how simple this question is. It's just going to take a little bit of time and then you're done. Super, super, super done. So change in internal energy of reaction equals 128.8123 kilojoule per mole. Of course, this question we can approximate. So I'm going to be doing this approximation in terms of two decimal places or four sig figs. I can do both. So in terms of two decimal places, we would end up with 128.81 kilojoule per mole. So this is in two decimal places. And if we're to do this in three sig figs, we're going to have change in internal energy of reaction to be 129 kilojoule per mole. So this is in three significant figures. So yeah, that's basically the end of this question. So I wish you guys all the very best. If you have any questions or suggestions or concerns, please put it in the comment section and I'm going to try my possible best to reach out to you immediately. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, given the reactions 1 and 2 below, determine the change in enthalpy of reaction as well as the change in internal energy of reaction for reactions 3. All reactions occur at 298 kelvins. So the first thing you have to note is this. Equation 1 is given to us, equation 2 is given to us, and equation 3 is given to us. So the reaction equation for 1, 2, and 3 are given to us. But we are asked to only determine the change in enthalpy for reaction 3. This is because we already have the change in enthalpy of reaction for equation 1 to be 52.96 kilojoule per mole, as well as the change in enthalpy of reaction for equation 2, which is negative 483.64 kilojoule per mole. The first thing you have to do is for you to observe, because what we're going to be using here to solve this question is called Hess law, or some people call it Hess's law. I'm not exactly sure, whatever you want to call it, just basically understand the law. What Hess's law does is we're going to manipulate the first two equations in such a way that we're going to get the third equation, right? It's like we need 4i, sorry, it's like this. We need to determine the equation 4hi gas plus O2 gas would give us or would produce 2i2 solid plus 2H2O gas. So we have to manipulate equation 1 and equation 2 in such a way that when we work with both equations, we're going to get equation 3. It's like simultaneous equation, right? So if you remember that in your middle school as well as in high school as well, you would notice that we have to manipulate it, meaning from a simultaneous equation, which is the technique we're going to be applying here. You see that we're going to have to cancel out some stuff. We're going to have to multiply some stuff. We're going to have to do we're going to have to switch both sides of the equation. We're going to have to multiply through by negative or multiply, sorry, we're going to have to multiply through by negative. Things like that is basically what we're going to be doing here. So the first thing we do is I'm going to rewrite the equation 3. So equation 3 here, we have 4hi, okay, plus O2 gas. So gas here as well would give you 2i2 solid plus 2H2O gas, right? Well, if you look at equation 1 and equation 2, you'll see that 2hi exists in equation 1, but it's on the right side of the equation. So what we have to do now is for equation 1, okay, remember 3 is what we're trying to get. So we're going to be using it to know how to manipulate equation 1 and 2. So for equation 1, switch both sides of the equation, okay, of equation. So what's not going to happen is that we're going to end up with 2hi, okay, let me use a red marker for equations. So we're going to have 2hi instead, gas, okay, would actually give us H2 gas plus I2 solid. And of course, anytime you switch equations mathematically, is the same thing as multiplying by -1. So now the updated change in enthalpy of reaction is going to be, the updated change in enthalpy of reaction is going to be -1 times 52.96 kilojoule per mole. So what we end up with is -52.96 kilojoule per mole. So that is the first manipulation. Now we have to reconnect and look at it again. What do we see? We see basically that the HI that we're dealing with here is 4HI. And then for equation one, we have 2HI. So the next instruction is going to be for you to multiply equation one, okay, by 2. When we multiply equation 1 by 2, this 2HI is going to become 4HI. So we're going to end up with 4HI. So gas will now give us, okay, 2H2 gas, okay, plus 2I2 solid. And when you look at our work, you're going to see thus far, we have been able to successfully um, get what is on the left side of the equation, right? This information here to match equation one. So equation three matches equation one for the molecule for each high gas, and then it also matches the molecule to I2 solid, and it also matches the direction. So it's both on the product side for equation one and equation two. So this is good. So now all we have to focus on is on oxygen gas as well as 2H2O gas. So the next thing is we have to look at equation two. How do we manipulate equation two to look like equation three? Well, from what we have here, we don't need to do any form of manipulation because the O2 for equation because the O2 gas for equation 3 matches the O2 gas for equation 3, right? So the O2 gas for equation 3 matches the O2 gas for equation 2. So these two match, and then the 2H2O gas matches that of equation for both equations match. So the H2H2O gas for equation 3 or reaction 3 matches the 2H2O gas for reaction 2. So basically this is okay. But before we go ahead, let's not forget that um for equation 1, even though we've multiplied by 2, we don't just leave the enthalpy of reaction just like that. We have to now multiply the enthalpy of reaction that we have negative 52.96 by 2. So that's going to be changing enthalpy of reaction. Since we multiplied it by 2 for the equation, we have to do the same thing for the number value. So that will be negative 105.92 kilojoule per mole. So this is basically how you solve this question. Now, we have equation 1, okay, and we have equation 2. So writing the information, let's rewrite equation 1 and equation 2. So equation 1 is now 4HI, okay, gas, so 2H2 gas, okay, plus 2I2 solid, and then equation 2 remains the same. We're not multiplying by anything, we're not switching both sides, it's going to remain the same. So we just have 2H2 gas. I hope you guys are understanding it so far. If you don't understand it, there's no issue. All you have to do is just like try to rewatch this video again. So 2H2 gas plus O2 gas is going to give us 2H2O gas. So now basically this is what you get. So anytime you have a situation, I've underlined 2H2, where a molecule in particular is appearing on both reactions on opposite sides of the equation, you have to take a good look at them. So you have a situation where in equation 1, 2H2 gas is on the product side, and then in equation 2, 2H2 gas is on the reactant side. That means they basically oppose each other. So all you have to do is just cancel them out. And hence you can now write your updated reaction for 3. So it's basically rewriting it. So what you end up with is 4HI, okay, gas, plus this O2 right here, O2 gas would give you 2I2 solid plus 2H2O gas. So this is basically the answer. And when you look at equation 3, what we were asked to solve for, we successfully solved for it. So that is number 3. So we're able to determine the equation. Now you're going to notice that I still haven't answered the question, changing enthalpy of reaction. Well, it's easy. The manipulations you did in equation 1 and equation 2 to find new equations. So, for example, now for changing enthalpy of a reaction for equation 1, we have 105.92 kilojoule per mole. And then changing enthalpy of reaction for equation 2, we have the same exact thing. It did not change because we did not manipulate the equation in any way. So it's still going to be negative 483.64 kilojoule per mole. So negative 483.64 kilojoule per mole. So that's basically what it is. So now I'm going to be wondering, okay, so what happens, right, to the enthalpy of reaction? Well, all you have to do is just simply add them up. So it's going to be 105 equation, sorry, enthalpy of reaction for equation 3 becomes adding enthalpy of reaction for equation 1 and then to equation 2. Okay. 105.92 kilojoule per mole plus negative 483.64 kilojoule per mole. So when you add them up, what you end up with changing enthalpy of reaction is going to be, oops, I almost missed something. Actually, rewriting this, I forgot to add the negative. So for reaction 1 is negative 105. So it's going to be negative 105. Sorry for the mistake. Imagine doing all this work just so you skip a minus sign. Please make sure you always look at your work. Even me as your tutor, I always have to cross check my work. So when you do this, you end up putting this information in the calculator to get negative 589.56 kilojoule per mole. And this is basically the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says C6H5COOH reacts with oxygen gas to produce carbon dioxide and water. So basically, this is a combustion reaction of C6H5COOH. So basically, we're asked to determine the change in enthalpy of the reaction when we're given the change in internal energy of the reaction. And we're also told that the reaction occurs at 298 kelvins. So basically, we've been given the change in internal energy of the reaction to be negative 772.7 kilojoule per mole. Okay. And we have been given temperature, which is 298 Kelvin, as well as we've been given the equation. So whenever you see a question like this, make sure you think about the general formula that says the change in enthalpy of the reaction minus the change in internal energy of the reaction is equal to the change in the number of gases for the reaction RT, which is gas constant times temperature. So when I see a question like this, and I've been given an equation as well as a temperature as well as the internal energy, I already know that this is the best equation for me to use. So the first thing is we already have been given the change in internal energy of the reaction, but we have to determine what this entire information is in order for us to substitute both of the information, which is the information on the right, as well as the change in internal energy, so we can determine the change in enthalpy of the reaction. So the first thing you do is for us to determine what's on the right, right? So I'm going to just put it on the information on the right here. So the change in the number of gases, okay, is just simply having the number of gases for the final state of the reaction minus the number of gases for the initial state of the reaction. So, yeah, that's basically it. So, the change in the number of gases for the reaction would be the change in the final state of the reaction, which is for me to just basically count the right side, the number of gases on the right side of the equation. So, you have 14 plus 6, that's 20, okay, minus the initial state, which is in this particular question, we see that we see that the C6H5COOH is a solid, so we do not even look at this in part of the information to determine the number of gases for the initial state of the reaction. For the reactant, we see that we have O2 gas and we have 15 molecules of O2 gas reacting in this particular reaction. So we have this. So that would be 20 minus 15. 20 minus 15 is going to just give us 5. So we know that the change in the number of gases for the reaction is just simply 5. So that's basically what's going on. So we have that, okay? So now we're going to just determine all of this. So that will be change in the number of gases, RT equals 5 times 8.3145 joule per mole Kelvin times temperature, which is 298 kelvins. So you just Basically, you cancel out kelvins. So you have 8.3145 times 298 times 5 would give you 12,388.605 joule per mole. So that's basically what's going to be the answer to this. So yeah, that's basically it. So now we have enough information that we can just input what we have to determine the change in enthalpy for this reaction. So we can rewrite the equation: change in enthalpy for this reaction equals change in the number of gas molecules, RT, okay, plus change in the internal energy of the reaction. So that's basically that. Well, we have one bit of an issue because we have the change in internal energy given to us on the question to be kilojoule per mole, and we have this information right here that we solved, changing NGRT to be in just joules per mole. So we have to convert this one to joules per mole. So I'm just going to write it. Sorry, we have to convert it from joules per mole to kilojoules per mole. So I'm just going to write the joules per mole part of the question up top. So this one here would just simply be 12.38861 kilojoule per mole. Okay, so that's what that is. So now we have all our information in kilojoules per mole. We can just simply substitute. So you have 12.38861, okay, kilojoule per mole minus, oh, sorry, plus the internal energy, which is negative 772.7 kilojoules per mole. So the change in enthalpy of reaction becomes negative 772.7 kilojoule per mole plus 12.38861 kilojoule per mole. When you put that in your calculator, you're going to end up getting negative 760.3114 kilojoule per mole. And of course, you can go on to estimate to approximate based on what we're given. So we've been given this question in 4 sig figs or in 1 decimal place, and we can just apply that same information to the answer for this question. So we end up having the change in enthalpy for the reaction to be negative 760.3 kilojoule per mole. So this is basically how you answer this question, and this is the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the change in enthalpy of reaction and the change in internal energy of reaction at 298 kelvins for the hydrogenation of ethine C2H2 to ethene C2H4. Ethine is an alkyne and ethene is an alkene. So we've also been given the equation that we're going to be working with, as well as the change in enthalpy of formation C2H2 gas. We've been given the value here. Actually, this particular question stops after the chemical equation. But in order for me to make this particular video easy, I decided to write out the change in enthalpy of formation for C2H2 gas, as well as the change in enthalpy of formation for C2H4 gas. So that is basically the information that I have thus far. So having this information is very key for you in an exam or in a quiz. They're going to give it to you, but in an assignment they expect you to go to the resource section of your book, or to go online and just Google the standard formation of whatever molecule your teacher asks you in the question. So in this particular case, this is not hard. In order for us to go and solve this question, the first thing you have to do is to write out the formula. Change in enthalpy of reaction is equal to the sum. So I'm just going to write out this equation and I'm going to explain it to you. So for products, reactants. So just looking at the work, you're going to observe that I wrote the exact same thing, and I wrote two of the exact same thing, right? The only difference is that the left side of the minus has products, the right side has reactant. So what this is telling you is that the change in enthalpy of reaction is equal to the sum of the change in enthalpy of formation for the product, okay, and then minus the sum for the change in enthalpy for of formation for the reactant. So I'm going to like basically write all of this information down. So the translation of this question in terms of this formula is just simply the change in enthalpy of reaction equals change in enthalpy of formation, okay, of the products. And our product here is just C2H4, which is ethene. So C2H4, okay, gas, okay, minus the sum of the enthalpy, so the sum of the change in enthalpy of formation for the reactant. So we're just going to say the change in enthalpy of formation for C2H2, because now we're dealing with reactants since we just had one product molecule, and then we have two reactant molecules. So we've done the one for ethene, and then that plus change in enthalpy of formation for the H2 gas molecule. As you can see, we have followed what the information here. So basically what we did here is that we translated whatever this information is up top, and we wrote it in terms of the question. So all you have to do is now substitute. So what you end up substituting is change in enthalpy of reaction is going to equal C2H4. We're just going to substitute whatever this is. So this is going to be 52.26 kilojoule per mole, okay, minus change in enthalpy of formation for C2H2 gas plus 226.73 kilojoule per mole, okay, plus 0. So that's basically it. Change in enthalpy of reaction becomes 52.26 kilojoule per mole minus 226.73 kilojoule per mole. So that's basically the question, right? So change in enthalpy of reaction ends up becoming 52.26 minus 226.73 becomes negative 174.47 kilojoule per mole. So this is basically the answer to the question. And as you can see, our question was given to us in two decimal places for both the change in enthalpy of formation for both ethene and ethine. So we can just feel comfortable that this is written in the answer is written in the correct format in two decimal places. So now we found this information, and the question actually just does not ask us for just change in enthalpy of reaction. A question also asks us for the change in internal energy of the reaction. So we're now going to use another formula to solve this. So first of all, whenever you see a question where you're given the change in enthalpy of reaction and then you're not given the change in internal energy, or you're given the change in internal energy of reaction and then you're not given the change in enthalpy of reaction, you're going to use this general formula here, which says change in enthalpy of reaction minus change in internal energy of reaction is equal to change in the number of gas molecules RT. That's basically what this is. Of course, you already know we have determined the change in enthalpy, okay, of a reaction, and we have that to be negative 174.47 kilojoule per mole. So if we can get this side of the equation, okay, now we have to find this side of the equation in order for us to find this one here, which is a change in internal energy of reaction. So we have change in the number of gas molecules, RT. Well, before we can do this, we have to first of all determine what is a change in the number of gas molecules. To do this, you have to go back to the equation. We're given a particular equation, and we're going to use this to solve this. To do that, first of all, before I go ahead and solve it, let me explain to you what's going to happen here. Okay, the change in the number of gas molecules is just going to be the number of gas molecules for the final state or for the product side, okay? So final state of reaction is basically the state of the product, as well as the number of gas molecules in the initial phase for the reactants. So that's just basically what's going to happen. So you're going to pick the number of gas molecules for the product minus the number of gas molecules for the reactant. So the number of gas molecules for the product is just simply one, C2H4. So that's just basically one gas molecule. So that we're just going to have that here. So one, okay, 1 minus change in the number of gas molecules for reactants. That's going to be We have one molecule of C2H2 as well as one molecule of H2 gas. So we have two here. So basically, change in the number of gas molecules is going to be -1. So yeah, that's it. So we're now just going to put this information here. So we have -1 times R, which is the common gas constant. So that's 8.3145 joule per mole Kelvin, times temperature, which is just, we're given that at the beginning of the class. So that's 298 kelvins. So times 298 kelvins. So yeah, let's cancel out the Kelvin, cancel out the Kelvin. So changing NGRT becomes -1 times 8.3145 times 298 kelvins, and that's going to give us -2477.72 joules per mole. Or we can just write it in kilojoules per mole, since, of course, change in enthalpy of reaction is in kilojoules per mole, and we're going to be using it soon. So it's best for you to keep the information in kilojoules per mole. So that's going to be -2.4772 kilojoule per mole. So going back to our math, we know that changing enthalpy of reaction is going to be, so we know that rewriting this in terms of changing internal energy of reaction. So we know changing internal energy of reaction is going to be changing enthalpy of reaction, okay, minus change in number of gas molecules, RT. So yeah, so we can put change in internal energy of reaction to be -174.47 kilojoules per mole. Okay, minus what we've gotten here, which is -2. Don't forget the other negative. So the information has negative and the formula has negative. So that would be -2.47772 kilojoule per mole. So what we end up with, change in internal energy of reaction is going to be -174.47 kilojoule per mole plus 2.4777 kilojoule per mole. So change in internal energy of reaction is going to be equal -171.9923 kilojoule per mole. And of course, we can do this in two sig figs to get change in internal energy of reaction to be -171.99 kilojoule per mole. Yeah, so I wish you guys all the very best. This is basically the answer to the question. If you have any questions, please put it for me in the comment section, and I'm going to try my possible best to help you. And you have any concerns as you're doing this class, make sure you put it in the comment section, as well as any suggestions you may have. Salam and welcome, everyone. So today we're going to be working on the question on the screen that says, for tetrachloromethane, the change in enthalpy of vaporization is equal to 30.0 kilojoule per mole. Calculate heat, work, change in enthalpy, as well as change in internal energy when 0.75 mole of tetrachloromethane is vaporized at 250 kelvins and 1 bar. The first thing you need to know is this. We've been given a question where we're told to determine heat as well as enthalpy in the same question. We have to understand that at constant pressure, heat is equivalent to the change in enthalpy. And we see that in this particular question, they did not tell us that the pressure was increased, it was decreased. They did not say the initial state was a particular number and then the final state was a particular number. They just told us that it's happening at 1 bar. So we can assume from this question that the pressure is constant. And because the pressure is constant, the heat as well as enthalpy will give us the same value. So what I'm trying to say is when we find heat, right, and we find enthalpy, we can simply, when we find heat or we find enthalpy, we can just simply know that finding one would equal the other. So that's basically what this is saying. Now, we're also told to find out work as well as change in internal energy. Note that by the time we determine the value for work, all we have to do is just remember that the change in internal energy is just Q plus W. So whatever the value for W is will be added to whatever we've solved for heat, and we will get the answer. So I just want to talk about the fact that this question should not scare anybody because it's a very fundamental question, and remembering the formulas that we've been using since we started this particular topic in physical chemistry is going to be the same thing you're going to be doing. So now, the only value we're given, right, um, aside from temperature and pressure, is the number of moles. So the values we're given aside from them are the number of moles as well as the change in enthalpy for vaporization. So the first thing you have to do is this. Remember that the units for heat as well as work is joules. So the units for heat, the unit for change in enthalpy, they are all joules. Okay, just joules. And this particular change in heat for vaporization is in kilojoule per mole. So what this is telling you is that enthalpy, okay, is just simply the change in vaporization for enthalpy times the number of moles. So this is what this is going to show you here. I'm just going to do the equation, and I'm only like breaking this down because I don't want to show people will be confused because they may be wondering like, okay, how did they go from here to here? So what I'm saying is the change in enthalpy is equal to the number of moles times the change in enthalpy of vaporization. Because if you remember, the unit for enthalpy or change in enthalpy is joules or kilojoules, okay? And then here is just simply the unit for change in enthalpy for vaporization is kilojoule per mole. So to go from the information on the left to the right, you have to use the number of moles. Or to go from the equation from the right to the left, you also have to use the number of moles. So in this particular question, we're just going to be multiplying the number of moles times the change in enthalpy for vaporization to get the change in enthalpy. So that's just how we're going to do. We're going to math it out. There's no major formula to go from changing enthalpy to changing enthalpy of vaporization. Just use the number of moles. So writing that out, we have changing enthalpy, which we're supposed to solve, is just the number of moles, which we've been told is 0.75 moles. Okay, remember that's what the question said, times the change in enthalpy for vaporization. So times 30.0 kilojoule per mole. So of course you cancel out the mole, cancel out the mole. So that would be 22.5 kilojoule. So that is basically the value or answer to enthalpy. And let's not forget, heat at constant pressure as well as change in enthalpy are the same value. So heat is therefore also going to be 22.5 kilojoule per mole. So yeah, that's basically what you do. If you want to stick to, yeah, that's basically what you do. That's 100% what you do. So we're going to stick to kilojoule per mole. We're not going to change it back to joules per mole. Doesn't really matter. That's just basically what we have. So the next thing we have to do is for us to determine work. Remember that generally the formula for work is negative P external or pressure, okay, that we're dealing with, times change in volume. But we also have to remember the chemistry behind this particular question. We're told that tetrachloromethane vaporized to go from liquid to vapor is gonna be basically a chemical reaction. So what I'm trying to say is to go from maybe having something in a container which is in liquid form, okay, to gaseous form is going to look like this. Everything vaporized. So maybe if there's a hood in the lab, you see the volume goes from whatever is in this liquid to everywhere. You can see that the volume is going to significantly increase as it's basically vaporizing. So it's going to go everywhere. It's just like how water can be small in a pot, but when you heat it so much and it starts to vaporize, the entire room feels steamy. That's because the volume of water has left the water has vaporized from the pot to everywhere in the room, and you can see the volume increases. This is the reason why you feel this steam all over, even though it might just be a small portion of water. So what this is telling you is this, that since you have this information, you cannot look at volume in the same way anymore, because the volume of the gas, right, has become significantly greater, right? Significantly, like much, much larger than the volume of the liquid. So than the initial volume. So the final volume of the gas is significantly greater than the initial volume of the gas. So knowing this information, we understand that the final volume is going to be approximately the change in volume. It's just like, say, the volume of the volume of the liquid before, say, initial volume was 5 milliliter. And then all of a sudden it goes from 5 millimeter to a million, okay, milliliter. Well, if you want to do the math, you would see that the final volume, which is here, would be significantly, meaning 1 million millimeter is significantly greater than 5 millimeter. So, what this is trying to tell you is that approximately the final volume is the change in volume, and we can represent this mathematically as basically rewriting the equation. So, we end up having work done equals negative P times V final. So, this is basically what we end up with. So, that's going to be the one that we're using. Now, we go back to our question. We remember that we're given pressure, right? 1 bar, but we were not in any way, shape, or form given the final volume. So we remember that the common formula that we started when we started with PChem is PV equals nRT. So since we don't know what the volume is because we're not given the initial or final volume or any volume, we can find whatever the value of VF is, but in terms of other parameters. So that means V here is now going to be nRT divided by P. So basically, that's just going to be what we're going to input. So rather than having W equals negative P VF, we're now going to have W equals negative P. So times nRT divided by P. Well, the pressure remains constant, the same value, so we can just simply cancel that out. So pressure cancel. So really work done ends up becoming W equals negative nRT. So what else are we going to do? We're just going to substitute. So W equals negative. What is the number of moles that we're given again? 0.70. Sorry, 0.75. So 0.75 mole. We're told the number of moles, sorry, the gas constant. We've been told the number of moles. So next we move on to the gas constant. So that will be 8.3145 joule per mole. Kelvin, and we've been told the temperature. If we go back to the question, we see temperature is 250 kelvins. Okay, so 250 kelvins. So of course, we do the math, cancel out of the units first, cancel out the Kelvin, the number of moles, and we just multiply. So that would be W equals negative 0.75 times 8.31415, right, times 250, all of that joules. So W equals negative 1558.969 joules. So that's basically what's going to be the answer right here. So of course, because we want to clean up our work, we can just do this in kilojoules, right? We can also determine the value in kilojoules. So that's going to be W equals negative 1.55897 kilojoule. So that's how you do it. Now, let's not forget that the change in internal energy, which is the last thing we're asked to solve for, is Q plus W. So going back to the question, you see that we're also asked to determine the change in internal energy. So we know that's Q plus W. We already know the value of our Q, which is simply 22.5 kilojoule per mole, as well as the value of our work. So we're just going to substitute. So you have change in internal energy equals 0.5 kilojoule, okay, plus minus negative 1.55897 kilojoule. So when you do this information, we end up getting 20.94103 kilojoule. So of course, we're given our initial question. We're given 3 sig figs for the change in enthalpy of vaporization. We're given 3 sig figs for number of moles and 3 sig figs for the value of temperature, and we use all of that information. So we have to put our final answer in 3 sig figs. So the change in internal energy becomes 20.9 kilojoules. So this is basically the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, when standard enthalpy of formation of ethyl benzene is negative 12.5 kilojoule per mole, calculate the standard enthalpy of combustion. So the first thing you have to do is the standard enthalpy of formation of ethyl benzene is this. We're told the standard enthalpy of ethyl benzene. So we're just going to say ethyl benzene is EB for now. So that would be standard enthalpy of formation. So like this, okay, of ethyl benzene. So EB is going to be equal to negative 12.5 kilojoule per mole. Now we're asked to calculate the standard enthalpy of combustion. Now, one thing you have to note is that in a combustion reaction, this is a reaction that occurs whenever a molecule is reacted with oxygen. So this was taught to you in your Gen Chem classes, and now you know that information that you're going to apply to this PChem course. So ethylbenzene is actually of the structure, even though the structure is not exactly what we need in this question, it's just going to be something that will help you anytime you're not given the actual structure or molecular formula, right? If you're not given the molecular formula, you can draw out the structure to determine whatever this is. So this is ethylbenzene. You have the benzene group right here, and then you have the ethyl group. Sorry, you have the ethyl group right here. So that's how it is. So yeah, you have the ethyl group right here, and then you have the benzene group right here. So this is basically ethylbenzene. So some of you may be wondering, why am I like being too like why am I like talking about every single thing like very intensely? It's because I want everyone to be able to be on the same page, because you need to be able to get every single part of this information in order for you to do well. So yeah, so we're gonna count now how many carbons and how many hydrogens we have, so that we'd be able to do the reaction. So you have one carbon, two carbon, three, four, five, six, seven, eight. So you end up with C8. Then we'll have to determine how many hydrogens. We know we've got two here. So this is CH2, we have CH3. So this place has five hydrogens. This place has no hydrogen because there are four bonds. So that would be one hydrogen here, another hydrogen here, third, fourth, and fifth. So five hydrogens plus the five hydrogens in ethyl group is going to give you 10 hydrogens. So you have C8H10. So rewriting this, we have C8H10 plus the combustion reaction, because we're asked to find the standard enthalpy of combustion for the reaction. So this one here, or the standard enthalpy of combustion, basically, yeah, for this particular reaction. So we're supposed to naturally, anytime you have a combustion reaction, you're supposed to always have carbon dioxide, CO2 gas, as well as H2O and water, which is in liquid form. So this ethylbenzene is a liquid, and of course oxygen gas is a gas. So now we're going to balance this chemical equation, because that's the next thing you have to do. So you can see that we're each inching into the question, right? Calculate the standard enthalpy of combustion. So now we're going to balance this equation. So you have eight carbons here. We have one carbon here. In order for us to balance it right, we're going to put an eight here. So now we have the carbons are balanced. We have oxygen here. 2 times 8 is 16. So we have the balanced carbon here, but we have then 16 oxygens here. And then we have how many hydrogens here? We have two hydrogens here. We have 10 hydrogens here. Well, 10 hydrogens and 2 here. In order for us to balance it, we know that 10 divided by 2 is 5. So we're going to put 5 here. So now we've balanced the hydrogen. So now we have the 10 here, and of course we have the 10 here. So now the only thing that remains for us to properly balance, in order for us to have a balanced chemical equation, is actually oxygen, because we're done with carbon, we're done with hydrogen, and both left and right side of the equation have the exact number of atoms. So next we have to determine the number of oxygens we have on both sides. We can see that on this side we only have two oxygens. On the left side we have two oxygens, right? And then on the right side we have eight. Sorry, 8 times 2 is 16. So we have 16 oxygens, and then we have for CO2, and then we have um five oxygens in the H2O. So that's five. So making a total of 21. And then we have two. How do we go from 2 to 21? Well, 21 divided by 2 is the same thing as 10.5. So we have 10.5 here, or we can just say 21 divided by 2. So when you look at all of this information, you would see that everything is balanced, right? We have a total of 8 carbons on both sides. We have a total of 10 hydrogens on both sides, and we have a total of 21 oxygens on both sides. So 21 divided by 2, this 2 you can think about it like you're canceling out, or you can just say 10.5 times 2, which is 21. So that will be 21 oxygens on both sides, right? And then this one, you have 16 plus 5. So that's a total of 21 oxygens on both sides, right? So that's it. So now we're just going to rewrite this equation. So that's basically our work. Since the combustion reaction is a reaction, you can just have, or since combustion is a reaction, you can have the change in enthalpy of combustion to equal this formula here, and I'm going to explain the formula to you. So you have this, and then you have the change in enthalpy of formation, okay, or change in standard enthalpy of formation minus this here as well. We're just going to write the same thing. But then you may be wondering, well, why are we writing the exact same thing? Well, this one is for products, okay, and this one is for the reactant. And this V here is just the stoichiometric value, meaning the coefficient or the stoichiometric coefficient. So this V here is going to be whatever is in front of the molecule. So if you have 2O2, this V here is going to be the stoichiometric coefficient of oxygen gas of O2, which in this case is 2. I'm just basically showing you what's going on here. So now we're just going to rewrite everything that we have. I'm going to break it down. We know now that we're going to sum up the standard enthalpy of formation of the product, and we subtract it from the standard enthalpy of the reactant. So this is what this is going to look like now. So we have this here equals 8 standard enthalpy of formation times CO2 gas plus 5 times standard enthalpy of formation of O2 gas, or H2O gas, sorry, H2O liquid. Why am I saying H2O gas? H2O liquid. So I'm just showing you what we're doing here. So you can see now that this first part of the information involved just the product. So the right side of the equation, the CO2, we have the coefficient at the front, and then the standard enthalpy of formation of just the CO2, while we brought the coefficient of CO2 to the front, and then plus we brought out the coefficient of H2O to the front, multiplied by standard enthalpy of formation. So basically, this is how you put down the structure of the information. Then you say minus, we're going to do the one for the reactants. So that would be enthalpy of formation of C8H10, okay, liquid, plus 21 over 2 is going to be brought forward. And then, of course, standard enthalpy of formation of O2 gas. So this is basically how it's done. This is how you structure or write out the structure of this part. Is very, if not the most important part of the question. So let's not forget that we've been given the standard enthalpy of formation for ethylbenzene. So this is the whole point. This is the reason why we have this. So let me rewrite the standard enthalpy of formation of ethylbenzene. So that would be that we had for EB here is the same thing as the standard enthalpy. If you look at your question again of C8H10, okay, liquid. So all of that information is negative 12.5 kilojoule per mole. I'm just rewriting it so that on this part of the question, you'll be able to know what you're doing. So yeah, so now let's go on to input the information and to substitute. We know now that 8 times the standard enthalpy of formation of CO2 gas. Some of you may be wondering, well, they only gave us the one for ethylbenzene. They did not give us the one for oxygen. They did not give us the one for H2O. They did not give us the one for CO2. Many times when you have questions like this, there's going to be a resource section of your textbook that has all of this information. So right now, they didn't give us the standard enthalpy for CO2. So if you're doing an assignment, you have to go to the resource section of your book and determine what the standard enthalpy of formation for CO2 is, and for H2O and for O2. They would not give it to you if it's an assignment. Maybe in a test or an exam, they're going to give you all the values for you to do it. Or maybe there's going to be a resource section for the quiz or for the exam. But just note that you can find this information on Google, or you can find it in the resource section of your textbook. Looking at textbook, I see that standard enthalpy of formation for CO2 is negative 393.51 kilojoule per mole. So I'm substituting. This is where I am right now. Okay, that is the standard enthalpy of formation for CO2 gas, plus 5 times the standard enthalpy of H2O gas. I'm right here now. So make sure you follow the resource section of your book. I'm purposely not writing it out separately for you guys because I want you guys to be actively searching for it as well. Because in an exam or in an assignment, you're not going to have me here writing out the information for you. So you have H2O, the standard enthalpy of formation. Looking at the research section of my textbook, I see that to be negative 285.83 kilojoule per mole. Okay, so that's that. And then that is the information here, minus the standard enthalpy for ethylbenzene. We're given this one, luckily, is just negative 12.5 kilojoule per mole. And then plus 21 over 2 times the standard enthalpy of formation for O2 gas. Looking at our information, we see that that is just simply zero, meaning everything right here is just zero. So of course, you input your information in your calculator. You have 8 times negative 393.51. We have that to be negative 3148.08 kilojoule per mole. Okay. Minus negative 1429.105 kilojoule per mole plus 12.5 kilojoule per mole. So yeah, all of this information right here would be standard enthalpy of combustion is going to equal negative 3148.08 minus negative 1429.15 kilojoule per mole will actually give you and all of that information plus 12.5 kilojoule per mole. So when you put all of this information in calculator, you end up getting negative 4564.73 kilojoule per mole. And as you can see, this information is in one decimal place. So you can just put this here and you can say the enthalpy of combustion that you're asked to solve is, and so yeah, standard enthalpy of combustion is negative 4564.7 kilojoule per mole in one decimal place. That is the answer to this question. Or you may be asked to solve this based on the fact that this is 12.5 kilojoule per mole in the question given to you, and that's 3 sig figs. You can also say the answer could be, depending on what you're asked to do, it could be in 3 sig figs, it could be in decimal places, whatever you're asked to do. So that would be negative in 3 sig figs, that would be negative 4.56 times 10 raised to the power of 3 K kilojoule per mole. And this is just basically the answer. If you're trying to be the best version of yourself with relation to academia, and you want to be the best student, or you want to be the best person you can be, basically fulfilling your potential and being successful in all your courses, especially the courses relating to STEM, make sure you email me at yourhobbytutoring@gmail.com. I am a personal tutor as well as mentor and educator for students who are striving to succeed in their academic life. So yeah, make sure you email me. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.